Okay, hi everyone. I guess that's audible. Can anyone confirm?
Yes, sir, you're audible.
Yeah, thanks. So, this is like a short uh, exposure to all of you, like as today's topic is real-time operating system. At the same time, we will be introducing to you what the EYRC thing is, which is the e-Yantra robotics competition. So, what you were seeing actually is the matchup film of e-Yantra robotics competition. So, yeah, this is how it is done. We'll show you the portal and things, but I will briefly tell you how it is done. So it's like it starts on August, and you all can enroll into this competition. And once you enroll, you will uh, you will be given a
Hello.
simulation task at various particular stages. It's not required that you need to know all of the basics
Uh,
everything.
Hello, am I audible?
Yeah.
Uh, I think there is mic on. Somebody's mic on. Hello, am I audible?
Yeah.
Uh, I think
Yeah, I think it's sorted now. So, yeah, once the task and simulation part is done, we alongside train you to do that particular task. So it's not like you need to come up with all the knowledge, but even if you have a programming skill or even if you don't have those skills which are required for the theme, you are given the learning resources. So that after each learning resources, the task is given to you in the simulation, and then you will have to go through it and a small task will be given. So when once the task is over, you will be evaluated, auto evaluated based on the submission. And once the submission is done, all the top rankers, all those who have been completed successfully and have achieved good marks, they will be selected for next stage. So the next stage is the hardware stage, wherein you will be given the hardware. So like the one you are seeing on the screen is a drone, which has to do mapping and geolocate obstacle on the road. So hardware will be shipped to you, and then you have to do the same task on the hardware. Yeah. Now I will share with you the website. So this is the website which is portal.yantra.org, wherein you can get all the details. So you see what is EYRC and will be briefly shown here.
Hey, Jason call.
And then there is a timeline given to you. So this timeline shows like you can get a brief idea that when the registration happens and what are the
But
stage
उसको
one
फिर
and
कैसे
stage two
unmute
and
करूँगा?
when the finale and all those things. So we can so how we will go in this manner. Like now,
नहीं आवाज
Siddharth,
कैसे
he will take care and
म्यूट ऑन
take
है
you
ठीक
through
है
the
हेलो आंटी
real-time operating system technical session, and then slowly we will go into MCQ session wherein you have to solve the MCQ based upon the things um, which were told in the presentation, and based on that you will be given the letter of participation. So yeah, over to you, Siddharth. You can start sharing your screen.
Hello, am I audible, Jason? Hello, Jason, am I audible? Hello, hello.
I have muted everybody. I think you'll have to unmute Siddharth.
Hello, am I audible?
Yeah, I can hear you.
Yes, you can hear me, right?
Yes, I can hear you, and
Okay.
yeah, people are also reacting to.
Yeah. Okay, great. I'll share my screen. Yeah, you can see my screen. Everyone. Yeah. Okay, so hello everyone. I'll start with the technical session now. I am Siddharth. I am currently working at the lab along with Jason and other members. So today I'll plan to go in detail about real-time operating systems, why they are used, how do we use them, why they are required, and some of the problems that they try to address. So let's start with the session. So as you can see, all of you must be familiar with embedded systems. So embedded systems are, you can see everywhere in your mobile phones, your cars, your microwave ovens, aeroplanes. Even most of you must be familiar with the Arduino programming interface and other Arduino related stuff that you must be doing. Maybe a line follower robot or something. All these are variations of embedded systems, are basically under the category of embedded systems. Even the router that you use, TV, remotes, everything includes embedded system. So in embedded systems, we have a small category called as real-time systems. A real-time system can be defined as an embedded system that reacts to an external stimuli in a time-bound manner. So what do you mean by that? So let's say you are driving a car and you press a brake. Now you want the car to slow down immediately. That is what happens if your car slows down after maybe 1 second or 2 seconds. You'll most likely have an accident. So you don't want any delay between your action and the response that you receive from the system. This type of system where you don't want any delay or you want a response within a specific time period is called as real-time systems. So real-time systems are systems which have stringent timing requirements. That is, you expect a response to be within a given time period. Not necessarily immediate, but can be maybe between 1 second to maybe 5 minutes. But a timing is fixed. You expect the response within that given time period. A real-time system can be we can distribute the real-time system into three small components that it consists of. One of them is sensors. So basically, when you have a real-time system, uh, your embedded system will need something to detect the external stimuli. The external stimuli can be something as simple as a button click, or something like a sensor reading, a temperature sensor, humidity sensor, or an encoder that you use with your robot or something. So basically a sensor that allows you to detect the changes in the external system. Then you require a processor. That processor will understand this input from the sensor and then decide what action needs to be taken. Let's say if it is a button press, then what action needs to be taken based on which button has been pressed. If it is a temperature sensor, then what temperature, based on the temperature reading, what action your system must take and other things. Finally, we'll need an actuator to bring about some change in our environment. So based on the changes that that the processor I detected using the sensors, we need some kind of medium by which our processor can enact output in our environment. Let's take a simple example of a automated system in a room. Let's say I have set up the system such that every time the temperature of the room exceeds 25 degree, the AC will turn on. Okay, so what we will need is we'll need a temperature sensor that falls under the first category. Then when the temperature sensor detects, this processor will read the data from the sensor. When the processor detects that the temperature has went above 25 degrees Celsius, it will use the actuators to start my AC. Okay, so this is a very simple example of an embedded system. We'll look into some more examples in details. Okay, so one of most fancy or common things that you must be seeing every day now is drones. So typically in drones, you have a wireless controller and you want to control the drone or how it flies or which direction it flies in using the joystick or using the RC controller that you have. So you don't want any latency. You want the feedback to be as fast as possible. You want the changes to reflect on drone as fast to be possible. That is one common example of real-time system. Then there is video conferencing, like the one that we are currently using, where like we are, for example, if there is some kind of jitter, you expect my information or whatever I am talking to be reached to you as fast as possible. Then similarly, there are Tesla automatic car systems or any automobile system, maybe your bike, maybe your car. All of these fall under the real-time systems. Another common example is the games that you play, maybe on your mobile, maybe on your PC. Now, when you try to, what you expect during the game is when you press a key on your keyboard or when you press on your screen, you wish the character to move or you wish some action to happen in a real-time manner. So these are some of the common examples of real-time systems. Now, what we'll try to do throughout this talk is we'll try to build up towards why we ever need an RTOS and what kind of problems we can solve using it. Do we need to implement it all kind of system? Should all embedded systems have real-time operating systems? We'll build up to that question. And to understand that, we'll take a closer look at some examples. So first example, let's say you're calling your sister or you are receiving a call from your sister. What if you press on the receive button, that the green button that you see on the screen, and after 5 seconds the call is picked up? What happens? You don't like it, obviously. There is a lot of latency between your action and the response that you are receiving. But still the call is getting picked up. But what happens if the delay increases to 1 hour? Every time you receive a call, you click on the receive button and after 1 hour the call is getting picked. Do you want that? No. So another example is video conferencing. So let's say I'm doing some actions and talking by seeing at the video. What happens if there is a little bit of frame drop? Instead of 60 FPS, you only see 30 FPS or something like that. So is that something that has broken the system? No, you can still hear me. You can still see them, get the message that I'm trying to convey, but you don't like the jitter or you don't like the lag in the system. So these kind of systems are called as soft real-time systems. So in soft real-time systems, their occasional delay or misses of deadline are allowed. So initially, remember what we talked about a real-time system is. A real-time system is a system where we are very sensitive to delays. We want every action to be done within a specified period of time. In soft real-time systems are type of real-time systems where occasional deadline misses are tolerable. As the deadline misses, the system does not fail, but a small there is a degrade in the quality. So for example, a printer, if you click on print and after let's say 5 minutes you get the print, that is fine. But if you get the print after 1 hour, that is a problem. So still the system gets the job done and the failure is not critical. However, the quality of the service degrades over time. So this type of system where a bit of tolerance is there, where we can miss the deadlines a few times, are called as real-time, soft real-time systems. Now, let's consider another example. So as most of you might be aware, the automotive industry is heavily driven by electronics and embedded systems. So your car, your vehicle, your bikes, all of them have lots of electronics in them, lots of microcontrollers in them that control different activities. One of such critical activities is the airbags. So what happens if you hit a car and it misses the deadline? So after your accident is done, it pops up the airbags after 5 seconds. Is that something that we can accept? No. So these type of systems are called as hard real-time systems. A very critical systems where missing a deadline leads to catastrophic or system failure, which is not at all desirable. So the hard real-time systems, you can see some of the examples like drones, rockets, stuff like that. So any sort of control algorithms that you run, different sensitive devices like pacemakers, which are located at your heart. So what happens if your pacemaker misses a bit or misses a deadline? It will lead to a catastrophic failure of the system. It will cause casualty or some harm to the patient. Similarly, we want systems like brakes and airbags to be as quick to response as possible. You don't want when you press the brake and your system stops after 5 seconds. You don't want that. You want your system, your vehicle, to slow down as you start pressing the brakes immediately at that instance. That might be within 1 millisecond, 2 milliseconds, or maybe half a millisecond. So these are the two categories of real-time systems that we talked about. One is soft real-time systems and a hard real-time system. So most of the systems that we design using our embedded systems like Arduino are kind of real-time systems. What we will try to do now is we'll try to make a simple robot using this concept. So we'll make a real-time system. We'll call our robot a small real-time system. What all things we want on this robot are, we want an IMU, an inertial measurement unit that will help me get the angular orientation of my robot. Then I want a wireless joystick through which I can connect the control the robot with. Then I want a display on which I want to show information. And on that display, I want to show this map where I want to show a map where I'll see all the things that are happening. So how would you do that in a traditional Arduino-like fashion? So I'm assuming everyone is familiar with Arduino. Still, we'll recap a bit. So what Arduino does is Arduino has these two functions. One is called as void setup and another is void loop. So so things that you want only to be executed once every time your system is powered on, you put in void setup. While the things that you want to be executed repeatedly in a cyclic manner are things that you put in the loop. So for example, starting up, initializing the screen, initializing the sensor, setting up all the parameters and etc. are something that is done in the setup. While things like checking for user input, driving the motors, checking sensors data and other things are done in the void loop. So to control a system like we talked about before, a system like this, what we will do is we will put we'll have something like a loop of this kind, where the first thing that our loop does is checks for sensor data. That it will check the IMU, it will check the encoders and whatever other sensor that our robot has to figure out what has happened with the system or what has happened in the environment around the robot. Now, based on this sensor data, we will try to, our control algorithm will try to figure out what action or what decision needs to be taken. Maybe there is an obstacle in front. Does my robot needs to stop? Whether there is some kind of activity happening near the robot that you need to address or some other things. Then based on the decision that your control algorithm makes, your motors will decide whether to start, your motors will respond to those. So let's say there is an obstacle in front of you and you need to stop the robot. The actuate motors function will stop the robot, give the necessary speed to the motors and other things. Now coming down, then we'll come to non-critical things like checking if the UI has been updated, updating the data on the UI based on whatever changes that we did in the first three instructions. We'll update the UI and then we'll check for user inputs and communications. So like you see in the diagram below, it is a cyclic process. One after the another, the task will get executed. So what's the problem here? So the problem with this system is the execution of the task one is dependent on the correct execution of the task before that. So if you look at the check external stimuli function, based on how long this function needs to takes to run or execute, is dependent on when my control algorithm will be run. So now what happens when my computer or my microcontroller is running this control algorithm function and at the same time my user presses a button? Now in this scenario, I will miss what the user has pressed because button click is instance, right? We don't hold the button for long. We just click it and we leave it. So what happens when my computer is executing something else and at that time I press a button? I will miss the input coming from the user, and user inputs are important. Maybe the user is clicking an emergency stop button and other things. So does this fit our definition of the real-time system that we talked about initially? So initially, yes. Okay. And that is fine. Okay. Yeah, it's fine. Okay, so we'll get back to the slide. Yeah, so basically each function is dependent on the other function. So it does not fit the definition of our real-time system that we designed before. That is the response. We cannot guarantee that response will be in time-bound manner. That is, we cannot say, let's say I want to run my control algorithm every 1 millisecond. Is that possible here? Can I guarantee that every 1 millisecond my control algorithm will be run? No, because I cannot guarantee when the how long the update UI button takes. Maybe I have to load some very graphic heavy image. In that scenario, the update UI button, update UI function will take, let's say, 1 second to execute. Now, because this update UI function took more long to execute, all the other functions are delayed. This will lead in me missing critical information coming from the sensors and also critical information coming from maybe the user. And in general, there will be latency in my robot. So basically, robot will crash to a wall or do something bad, not listen to user inputs and other things. So how can we make this system such that we can respond in a time-bound manner, such that my control algorithm, which is the most important thing for my robot, is executed exactly 1 millisecond at the rate of 1 millisecond. So one common approach to this kind of situations is interrupts. So in embedded systems, we have this mechanism called as interrupt. So like you see here in this diagram, this is a diagram that open source diagram that you can find on internet. But in this diagram, there are a bunch of instructions and the computer, this is the loop. So the computer goes in executing instructions one after the another. And whenever an external particular event occurs, like maybe a button press or maybe some sensor data or something, the code flow is interrupted. It will jump to other location, execute the particular instructions that are designated for that event, and go back to the first cycle. So it's similar to how we work in our day-to-day lives. Let's say someone has given you some task. That is at 12 o'clock in the morning, you have to go and switch on a particular motor or switch on a particular fan. Do you wait there looking at the clock? Is it 12? Is it 12? Is it 12? No. What do you do is you put an alarm on your phone or whatever mechanism that you have, and then you continue working on your work. But the moment it is 12 o'clock and the alarm rings, you interrupt your work, you go to that place, turn on your phone, turn on your motor, your fan, whatever, and get back to your work. The same concept is employed here, where we configure our computer or our microcontroller to react to these particular events called as interrupts, where when a particular event like a button press or maybe a sensor data reading or something occurs, our flow of the loop will be interrupted. It will go execute those specified steps first and then come back to the original execution. So it will look something like this that you see on the left, where right now, if you look closely, you will realize that the control algorithm function is no longer in the loop. I've configured my timers. So timer is another mechanism that you can use to drive the interrupts. So timer is something by which you can configure at what intervals you want a particular function to run. So microcontrollers have multiple timers built inside them, and you can use them in various ways. So here we'll configure the timer such that at every 1 millisecond, my control algorithm function is run. So I have in the void setup, like we talked before, I have set up my timer to run the particular control algorithm function. Now my loop will start executing the check sensors function, actuate motors function with and everything like we planned before. And after every 1 millisecond, my microcontroller will jump to the ISR, that is the interrupt service routine, execute the control algorithm, go back. Now now when another 1 second elapses, it will interrupt the loop again. It will go back to control algorithm, execute the function again, then go back to the loop, and this cycle continues. What this does is this kind of mechanism allows us to guarantee that after every 1 millisecond or whatever time that you are working with, maybe 50 milliseconds, or maybe 100 milliseconds or maybe 1 second, you can guarantee that after every 1 second or that time period that you mentioned, your control algorithm function will be used. Great. So we guarantee that it has become a time respondent real-time system where we can guarantee that a particular task will be responded to in a timely manner. Now, why don't we do that to all of this? The problem with doing that is an MCU has limited number of timers, so a limited number of interrupts. And so we cannot put all the functions that we have in multiple interrupts and keep on working them, because these timers are also used for other functionalities. So what we will do now is there is another challenge here as well. The timers are not portable and are not very flexible. So anyone who has written a code for timer, you realize that it is a very tedious job. You have to read a bunch of data sheets, then configure the timer properly to work at a particular rate and stuff like that. Also, if you write a timer code for, let's say, your Arduino Uno, it won't work for ESP32. If you write timer code for your another microcontroller, let's say STM32, it won't work with Arduino Uno. So there is a bunch of compatibility even between the microcontrollers from the same company. So configuring a timer is a tedious job. And anytime then I have to make changes to the code. Let's say I want to change the sequence or change the rate at which I want a particular function to execute. I have to again reconfigure the timers, and it is a bit of a hassle. So that's where the real-time operating system comes in. So real-time operating system was designed so that we get this timer interrupt like behavior using timers without having to deal with all this low-level hardware integration stuff. So one simple solution to all of this can be, what if we could have multiple loops? So that is something that RTOS helps us with. So RTOS has these mechanisms or units called as tasks. Each task is like a mini program having its own loop. So let's say our task 1 is our control algorithm, task 1 is our sensor data, task 2 is our control algorithm, and task 3 is our update UI. So what RTOS does is RTOS will treat it like three separate programs, and it will have 3 different void loops or 3 different while ones that will keep on executing. And what our real-time operating system does is it switches between these tasks such that all of them are executed. Okay, so maybe one after the another, it will schedule it properly. So here we'll come back to the snippets again and again, but let's address this for a while. So currently during this session, we'll be talking about free RTOS. So free RTOS is like an open source RTOS that is Arduino compatible and you can work it with your ESP32. So this is a simple example of the task that we need created using free RTOS and Arduino IDE. If you look here in my void setup, I have these three functions. One is the X create pinned task pinned to core. That is, I'm creating a task and pinning it to a core. ESP32 has cores, and basically it's a function in this is a function that allows me to create a task. Okay, so the first one is the function that we want to execute that you can see on the right hand side, that is here. That is void sensor task. You can see it here. Then there is a name of the task. Then there is a stack size. We won't get into the memory management detail, but stack is the type of memory and you can read about it on your own. Then there are parameters, if any. We don't have any parameters. And there is a priority. So what is priority? We'll read about what is priority in the coming slides, but this is how you basically create a task. So for our example, what we needed was we needed three tasks. First was the sensor data reading. Second was the control algorithm. Third was the update UI task. So if you look at the right hand side, sensor task has its own while loop. Control task has its own while loop, while the UI task has its own while loop. Now, what does the other parameters in this thing means? We'll come come back slowly. Okay, so now since we have these three tasks, you see a number called as priority. So the problem comes, how does our RTOS know when to execute which task and for how long each task is running? For that, we have these mechanisms called as ticks. So what RTOS uses is ticks are basically uniform chunks of time. So they divide the total time that we have, maybe let's say 1 second, 2 seconds, etc., into uniform chunks and call them ticks. Each tick is of 1 millisecond. Okay, so using this ticks, the RTOS will be able to figure out for how long and each particular individual task is running. For how long, for example, task 1, that is our sensor data read, is running. Then task 2, that is our control data is running, and other things. Based on this information, now it will decide how to run it. So what task priorities do is we can configure some task to have higher priority than them. We can say that this task is much more important, and whenever this task wants to run, we'll we'll give it the computational resources to run. So as you can see in the table here, the emergency stop, we want our robot to stop immediately as soon as I press the emergency stop button. So emergency stop will have the highest priority, that will be 5. Control algorithm will have 4, 3, and 1. So similarly, you can give priorities starting from 1 to 5. 5 is the highest priority that you can give in free RTOS. 4 will be the second highest priority, 3, and so on. You get the idea. So what the priority tells the RTOS is which task it should give priority to, which task it should run first. Okay, so what will RTOS do is RTOS will run the highest priority task first. And the lower priority task only runs when the highest priority tasks are executed and the computer or the microcontroller has nothing more important to do. So if you take a look at the photo here, our task 2 is the least important task. Task 2 is a lower priority task as compared to task 1, while task 1 is the highest priority task. So if you look at the diagram closely, you'll see that for the first millisecond, there is nothing more important to run. So task 2 is executed. So what does RTOS do here? So at the start of each tick, that is at the start of each tick, the RTOS will check if there is a higher priority task or what is the highest priority task that is waiting to run. So when we say when task 2 when it finds that task 2 is the highest priority task currently that is available to run, it will start running the task 2. Now after the one tick has elapsed, the RTOS will the RTOS will come in between again. It will check if there is some other higher priority task running. If not, it will then let task 2 continue. You see that in the first 2 ticks, after the 2 ticks, task 1 is ready to run, which has higher priority than task 2. So now RTOS will switch the computer from task 2 to task 1, and the task 1 will get executed. Since task 1 has the highest priority, till the entirety of task 1 is completed, task 2 does not get the compute time. Now once task 1 is completed, that RTOS hands back the control back to the task 2 so that the execution can continue. And finally, after the task 2 has concluded, task 3 starts running. Okay, so based on the priority, RTOS decides if which task interrupts what task. Since task 1 has the highest priority, it interrupted the task 2. And once task 1 was done, task 2 continued. Since task 2 had higher priority, task 3 did not start till the task 2 was completed. Once task 2 got completed, task 3 started execution. Okay, so what if two tasks have the same priority? Let's assume that task 1 and task 2 have the same priority. What will happen then? So at that, in scenarios like this, what the RTOS will do is execute them in round robin fashion. What do we mean by round robin fashion is they will take turns using the resources of the computer for execution. So let's say we start with task 2, then task 1 will be executed, then for one tick task 2 will be executed, and so on. And once both of them are finished, task 3 starts execution. Okay. So this kind of round robin scheduling approach is used to ensure that both the tasks which have equal priority get the enough CPU time to execute properly. Okay, these both tasks take turn using the resources such that they can both complete their execution in a timely manner and the deadlines that are given are met. Okay, so what happens when my task 1 keeps on running? My other task will never get a chance to run. So when lower priority tasks are scheduled to run is basically when there is nothing more important to be done. So if there is free time or some high priority task is waiting on idle, that is waiting to receive some data, etc. So high priority task getting blocked is a terminology that is used in RTOS. So what do you mean by blocked? Blocked means when a high priority task is or any task is waiting for an input from maybe an external device or maybe from another task or something like that. It is waiting for an input, waiting for a data and other things. During this time, the task is idle, and in such conditions, a lower priority task is executed. But we have to make sure that whenever we run the lower priority task, the tasks that do not have the real-time requirement are put there. So anything that is catastrophic to our system, we won't put as a lower priority task. For example, emergency switch, although the task might be very small, very minimal, we'll put it as a highest priority because we cannot afford the task getting delayed. Okay, so now there is this question: what type of task would you put in a lower priority as a lower priority task? So typically, in most of the systems, responding to UI or generating a UI is pretty intensive, and hence it is put in a lower priority task because the UI is just an user interface for the user. For a user, 1 second is a very small time, but for my system, 1 second is a big time. So these UI related tasks or something that is oriented towards graphics are generally put in lower priorities because even if there is slight delay of maybe 50, 20 milliseconds in execution of that task, it won't directly affect my user because it is too fast or it is too small for my user to notice. So tasks that are non-critical and take longer to execute or longer to execute but minimal in context of the user are kept as lower priority. Okay, so how do we design higher priority task? If we are not careful while designing the higher priority task, the problem is our higher priority task will never give access of the computer or the microcontroller to our lower priority task at all. So there are four key problems or four key points that we need to remember here. First is keep the task short. Higher priority tasks should be executed quickly and the code should be able to exit from them quickly. There should be no delays or time consuming operations there. That is drawing something or maybe infinite loops and things like that. We do not put them in higher priority tasks. We also do not use the delay function there. We have to make sure that we don't put blocking conditions. Like conditions like, oh, while this sensor data not there, then keep in the loop and things like that. We do not put in the higher priority task. And we yield often. So the concept of yield is whenever my computer, let's say my higher priority task gets executed 2 times. Now, it has met all his deadlines. So what my higher priority task can do is it can yield, that is give up control voluntarily so that other low priority tasks can complete their execution. This happens when this can be done when your higher priority task has done multiple rounds of execution already and you are satisfied and has met all its deadlines. So this kind of condition is called as yield, typically represented by a yield function that you must have used with your Arduino as well. Okay, so we'll come back to the slide that we saw before. So in this slide, now you can see the vtask delay button, vtask delay function on the right hand side. This v task delay means that after executing once, I'm setting a timeout for this task. So for another 100 milliseconds or another given time, 100 milliseconds, the task won't be executed. Okay, so what I am doing is I am basically, once the task is executed, I am putting a timeout. I am saying once this task is executed, I do not need to look at this task for another 100 milliseconds, because that is the requirement of my system. If your system requires frequent use of a particular task, you can reduce this v task delay or remove the v task delay entirely. But you have to be sure that you do that you yield the control, that is, you give the control voluntarily from your higher priority task to the lower priority task, so that the execution of all the task is completed. Because in a real-time systems, we have multiple loops or multiple tasks that are important for the proper functionality of our system. Okay, so another problem that we noticed when we are talking about before. Now this is all great, but still we will need to get some work done, right? We have these different tasks, but typically we have a global variable, and then we try to send data between. Then the global variable is updated. Then our other functions use this global variable to check if a particular value has increased a threshold. Like let's say maybe the temperature has increased or something, and based on that decisions are taken. So how do we do that in our RTOS or real-time operating systems? Can't we just use global variables? So the problem is, no, we cannot use the global variables, because we cannot determine if the global variable that we are going to use is not being used by the task, some other task currently. So when you try to, let's assume a global variable called as float A. So float A is being written to by a task called as by our sensor task. So the sensor task basically reads the data from the sensor and writes it into a global variable called float A. And our control task reads the global variable float A and executes its control algorithm based on that. Okay, so the problem here is my control task won't ever know if the data that he is reading from float A is the updated one, is the latest one, or if it is being overwritten by the sensor task again. To make sure that there are no conflicts, that we always read the updated data or data in a sequential manner, there are these mechanisms called as queues. So queue, like you must be familiar with most in your data structures and algorithms course, are first in first out data structures. So the first message that you pass will be put in the front, that will be removed, and that will be removed by the receiver and processed. Then the second message. So the first thing that you put in is the first thing to go out. So this structure is used to send variables or send information between two tasks. So let's assume that the task A is our sensor data task and task B is our control algorithm task. So what task A will do is every time it takes the data from the sensors, processes it, and the data is ready, it will push it into the queue. Let's assume the one is the number one is the latest data that is pushed, and task B will read the data one by one from the queue. So this ensures that we do not read half-written data, or two variables, two tasks do not try to access the same memory location at the same time, because that can cause problems. Okay, so if we have two tasks, this is how we'll share data between them. We'll use a data structure called as, we'll use a function mechanism called as queue, which will allow us to send data sequentially to other tasks. Now, one important technical terminology, this is called as thread safe behavior. So global variables are not thread safe, queues are thread safe, and this ensures that we get the data sequentially and on other parameters. Going ahead, now what happens, we have these multiple hardware peripherals. Let's say we have a display, we have the UART bus, we have encoders, we have sensor data and other things. We have an I2C bus and other communication protocols. What if two tasks try to access the same thing at the same time? What if two of my tasks try to write to the display at the same moment? What will happen? It will cause conflicts. So these kind of situations are called as race conditions, when two or more tasks try to access the same resource at the same time. To solve these conditions, to solve this problem, we have this mechanism called as mutex. So mutex is like a key to a lock. So let's assume this is a very common example, has been used multiple times in online videos and stuff. Is like you have this common resource, maybe is some shared washroom in your college. It has a key, the washroom has a lock and a key. So whenever a person goes in, he takes the key, opens the lock, uses the washroom and comes back. Till the person comes back, there is no key, so the another person cannot access the washroom at all. When the first person comes out, then only the other person can use the key to access the washroom or whatever the shared resources. in our scenario, let's assume the shared resource is a UART bus. So let's say my task A wants to send something over UART and task B also wants to send something over UART. So task A comes there first. It takes the mutex and goes into execution. So it starts using the UART to send some data. Only after task A is done executing, then only task B can execute. The task B can take the mutex and execute the UART again. This is depicted very nicely in the graphic that you see here, where on the left hand side you can see a mutex box where a dot represents a mutex. So whenever task B tries to get, whenever task A wants to take the mutex, it access the shared resource. It will take the mutex, use the shared resource, and at the same time, if task B want to access it, it won't be able to access it because the mutex is already taken. You can see that in the graphic below. So this X semaphore take, the X mutex give, and other functions are inbuilt functions that are present in free RTOS. There is intensive documentation of all these functionalities in the free RTOS official website, which you can refer. The idea behind this talk is we'll introduce you to the different mechanisms that we have in the RTOS and when we should use what. As you have seen in the graphic, we'll move on to the next slide now. So there is this question, what happens when a low priority task gets a mutex on a higher priority task? Let's say my higher priority task, that is task A, is wants to use the UART, but at the same time, task B has already got the mutex there and is running and is using the guarded resource. Now my task A, which is the highest priority task, is waiting on my task B to complete. So my higher priority task is waiting for a lower priority task. This is not a desired behavior. This kind of condition is called as priority inversion. So we won't get into much more details about it, but priority inversion is one of the topics that has been addressed a lot in the real-time operating systems, and there are multiple ways to tackle it, majorly via priority inheritance and other protocols, but this is one of the issues that you might face going ahead. Another most important mechanism is called a semaphore. So semaphore is basically a way for us to signal another task. So it is a process by which one task can signal another task to start. So there are two. We'll go into a detailed example which will make things more clear. The first thing is binary semaphore, and second option is counting semaphore. So binary semaphore is basically like a flag. Let's say I want to start a particular task, maybe after 1 second, or maybe when a particular button is pressed. So let's say I have a button on my system. Only when that particular button is pressed, I want task A to start execution. In this scenario, I can use a binary semaphore. So whenever the button is pressed, I can have an interrupt on that button, and whenever the button is pressed, the binary semaphore will give the flag to the task. Once the task receives the semaphore, it will start executing. So to trigger this kind of automatic behavior on the run, you can use semaphores. So sometimes let's say you have this big robot which has a big screen, or you have a robot which has some critical functionality that you only want to start maybe half an hour later, or when a particular event occurs. In this kind of condition scenarios, you can use the binary semaphore. What you can do is, let's say I want to start the screen only when the user presses the start button. So what will happen when I press the start button? The interrupt will be executed, and in the interrupt I will give the semaphore, that is I will give the signal to the task to start execution. So only then the task will start executing and come into the loop of all the real-time operating system stuff. Now coming towards another thing, counting semaphores. So binary semaphore is something that only one task can take. So let's say I have two tasks that want a semaphore. Only binary semaphore is like a small key I can give to only one of them at a time. Unless the first task returns the semaphore, I cannot give it to someone else. It is similar. Binary semaphore in that context is a bit similar to mutex, but they have very fundamentally different use cases. Now coming towards counting semaphores. So to explain counting semaphores, I'm going to use this small image that has been developed by DigiKey. So you can find this on their website as well. So let's say I have a shared resource that is maybe a linked list, a buffer or something, where I want to store the data which can be used by someone else later. So task A and task B are developing something or doing some process by which they are generating two values, and they are putting these values in the shared resource, and task C and task D are my consumers. So task A and task B are my producers, and task C and task D are my consumers. Task C and Task D will utilize this data to make their own decisions or do their own functionality or something like that. While Task A and Task B will produce the data that will be used by them. So in this scenario, what we will do is Task A and Task B will put the data here. This will increase, will give the semaphore. This will increase the count here. So right now I have two values. So the count semaphore is 2. The moment Task C takes one data, the first data is taken by Task C. Now the count reduces to 1. So right now, then when Task D takes another data, the count of semaphore will go down to 0. Now in this scenario, if another task, let's say task F, comes into picture and tries to get the data, will it get the access to the buffer? No, because both of the data have already been used, or semaphore for both of them is taken. So based on how much data is there, I can decide how many tasks or how many resources how many units can access the same resource at a time. In this scenario, we only wanted 2 tasks to access the resource at the same time. Both the semaphores are given, hence no one else will be able to access the given semaphore. So this is what semaphore is. It might look very similar to queue. It is. So in most cases where you can get away by using a queue, I would recommend that you use a queue. Semaphores are very great in signaling between the tasks, but they are used in mostly complex scenarios. So here is a simple example of implementing a binary semaphore. So semaphore x give and is basically a function, is an internal function that is given by the free RTOS. This is all written in Arduino. So here you can see I don't have a void loop at all. So I have this sender task and I have a receiver task. So when my sender task starts running, when my sender task sends a semaphore, then my receiver task receives it and executes it. Until and unless my receiver task gets a semaphore from the sender task, it won't execute it. I hope this clears everything up regarding semaphores. Okay, so coming towards an important question, do you need RTOS at all? So since we have been talking about RTOS for a while, should we include RTOS in all of our projects? The answer is no, because the Arduino and even the Arduino or a smaller microcontroller has 16 megahertz of clocks. That is, it means it can execute up to approximately about 16 million instructions per second. So your loop, let's assume you have an empty loop. That empty loop will be has, let's say, one instruction. Your loop has one instruction. It will execute that instruction 16 million times within 1 second. So in most scenarios, a single loop or super loop application is more than enough for most of your projects. That is, maybe you have a small line following robot, or maybe you have a data logger system, or some water ATM, or some other kind of project that you will be doing for your 3rd year, 4th year, or maybe as your final year project. These systems are more than sufficient to be run on a super loop system, where you can leverage the mechanisms like interrupt and other things to make sure that your system responds properly. But when you have multiple time critical activities, like we saw in our robot example, we have multiple time critical activities that were like reading the sensor data, looking at the emergency stop, etc. If you look at our automobile, look at our car, it has multiple time critical systems. Like it has a airbags, it has brakes, it has engine RPM control, it has, maybe if you are talking about the Tesla, then it has this automatic navigation and stuff like that. So in scenarios like this, where you have multiple time critical systems, that is where you will use an RTOS, and that is where you will benefit it with the most. So another revelation for you guys is you are currently using RTOS. If you are working with ESP32, most of the ESP32 libraries, the Wi-Fi library, the Bluetooth library that you use, already use the RTOS internally. If you have ever used the yield function of ESP32, it has been using the RTOS internally, but you are just using it with an Arduino wrapper on top of it. So typically RTOS is very widely used in network applications, because network stacks are very memory intensive. So maybe if you have a Bluetooth communication, maybe if you have a Wi-Fi communication, a Zigbee communication, these network stacks are handled usually very well with Wi-Fi, with RTOS. So some of the RTOS, like today we talked majorly about free RTOS, and there are some other options as well. There is Chibi RTOS, there is ARM Embed, although I'm not sure if the ARM Embed is supported anymore. There is Zephyr RTOS, and there are other open source alternatives as well. So while concluding, I would like to just mention one thing, that be careful about which applications that you use RTOS for, and use them for appropriate behavior. It is a very nice tool that if used properly can increase the performance of your system, but not all systems needs to work with an RTOS. So I guess I'll open up for questions now. If you have any questions, you can raise your hand or type in the chat. Okay.
Yeah, so if you have any questions, just put it on the chat, and we can take up all the questions till 5:55, and then we'll have a 5-minute MCQ.
Explain about semaphore once again. Okay, so I'll share my screen again. Okay, hope you can see the screen. Yeah. So there are two types of semaphores. One is a binary semaphore. Second is one is an binary semaphore. Second is an counting semaphore. So what does a binary semaphore means is when we use a binary semaphore, let's say I don't want all my tasks. So like you saw in the example before, in this example, we created all our tasks at the same time, and all of them started execution at a moment. But what if I want one of the tasks to start execution after a particular event has happened? The event can be anything. The event can be maybe a button press, maybe some kind of activity or some kind of sensor input or anything. In scenarios like this, where you want to start one of the tasks a bit later, or only want to execute that task when a particular event happens, something like an interrupt or something, and that is when you will use a binary semaphore. So if you look at the code here, this is the binary semaphore. So unless sender one, that is my task, one task indicates to another task, give an instruction to another task, it won't receive a task, it won't start execution at all. So this is the binary semaphore. So now let's say I have a linked list. So all of you must be familiar with linked list. So what I want to do is I have a linked list, and in the linked list, two of my tasks are putting in data. So let's assume that task A and task B are reading the data from two sensors. Both of them are temperature sensors. Okay, so I'll come to questions one by one. So task A is executing, getting the sensor data from temperature sensor 1. Task B is getting the temperature sensor data from temperature sensor 2, and both of them will put it in the linked list. Now, if since there are only two updated datas, I would only want I only have two copies to share with other tasks. So that is what semaphore does. So based on how many semaphores it has, it will have a count. That is it. Maybe currently I have two values, or currently I have two semaphores. So two tasks can read the data from me. So when the task C reads the data from it, then the semaphore goes down to 1. When task D reads the data from it, the semaphore goes down to 2. This is called as counting semaphore. When task A gives task A and task B again give the data back, then when task B gives the data back, the semaphore count will increase to 1. When task A gives the data back, the semaphore count will increase to 2. In most scenarios, you don't need counting. You won't need a counting semaphore. You are well off with using a queue. Okay. You explain embed. Why I can't use global variables? Okay. I'll start with yield function again. So yield function is basically let's say I have a higher priority task. So higher priority task is running. It has run multiple times already. So it is satisfied with the current rate at which it has executed, and it can wait idle for some time. In scenarios like this, a yield function is called. This function is used by the higher priority task to basically give up the control. It will say, I have executed enough times. Now let some low priority task run for a while. Then when I'm ready again, I'll start executing again. That is the function of a yield function. Why can't we use global variables? Okay, great question. Basically, there are multiple data types, right? So each data types, let's assume that I have a long data type that is a very big integer. So long data types typically has 8 bytes of size, or whatever system that you are using on. 8 bytes of data cannot be read in a single instruction by most of the microcontrollers. Let's say I have a microcontroller, 32-bit microcontrollers, it can only read 4 bytes of data at the same time. So to read the long variable, it will read or write to the long variable. It will take 2 cycles. That is, in the first instruction cycle, it will get the first half of the data. In the second instruction cycle, it will get the second half of the data. So in this scenario, when my task A, for example, is writing to the long variable, in the first iteration, it writes half of the data. In the second iteration, it will try to write another half of the data. But before it writes another half, let's say my another task reads the data. What happens now? The task that read the data has read one of the updated data and one of the older data. Now that is the problem with using global variables. Okay, for using RTOS, do we ensure a backup to it if it fails to function? Yes, you can. It's dependent on how you design your system. To execute the interrupt, do we run a separate loop to check for inputs? No, what you have just mentioned, the question is to execute the interrupt, do we run a separate loop to check for inputs? No. So when you do run a loop to check for input, that is called as polling. So polling is pretty computationally expensive. It's like a small kid waiting. If you tell a small kid that at 10 o'clock, I'll give you chocolate, it will keep on asking you, is it 10, is it 10, is it 10? And that is problematic. We don't want our computer to behave like a small kid. We want to be smart about using our resources. So what interrupt is more like a mature man, how it will wait. It will put an alarm. So whenever there is alarm, a particular mechanism will be triggered. You don't have to check for it in your loop or in your some kind of task to make sure that the interrupt is happening. The interrupt will automatically get called. Okay. As the name suggests, it is OS like Windows Linux. Most of the cases, this one is already installed. Okay, so for example, they are saying is not exactly true. So RTOS basically means real-time operating system. So operating systems are generally used to handle multiple things, file system, display, UI, and the general purpose operating systems that you work with are designed for users. So if you look at our operating system, maybe Linux or maybe your Windows or something, then they are designed to so that you have the best experience. While the real-time operating system does not care about all the tasks executing properly. So in general OS, each task has equal weightage and are executed one by one. In real-time operating system, the highest priority task is always has the most highest priority and will be executed all above all. So it won't try to, unless you program it smartly, it won't try to switch between the tasks so that all of them are equal. No, it treats one better than the other because it is a time critical system. Why can't we use global variable? I hope that I answered that question. Gazebo is not responding. Okay, you can ask that question in roster related thing. Can you give an example where you use semaphore and mutex as both of them seem a bit familiar? Okay, great. So mutex is basically semaphore. Let's forget about semaphore for now. So whenever you want to, you have a UART bus or you have a display. Display is a simpler example. You have to write to a display. Whenever you send the data to the display, it prints something on the screen. Okay, so I have a task who wants to update the data on the display. He tries to send the data. At the same time, another task also tries to send the data to the display. What will happen? There it will cause problems. None of them will be able to write it. So this is where mutex comes into the picture. So mutex is like a lock. So whenever someone is using the mutex, it tells it, oh, I'm using this particular hardware resource. So till he comes back, no one else is able to use the display. So let's say task A gets a mutex on the display. Till task A is done with the execution, no other task will be allowed to get to the display. Once task execution is done, it will return the mutex, and then this mutex will be used by other tasks to execute the display. Okay, so mutex is like a key to our lock. Okay, so one loop to rule them all is basically a super loop. That is something that you do in your Arduino IDE. And typically when you use void loop, it is basically instead of, right now we have 3 different loops that are executed one by one, etc. In super loop, that is that one loop to rule them all is basically only a single loop, like we saw in the slide before, only functions will be executed one after the another rather than parallel. In RTOS, we try to run them parallelly. Let we manage our compute so that all of the functions, all of the tasks are executed together. Okay, I hope I answered Srujoy's question. how does free RTOS, how does task scheduling priority in free RTOS ESP to interact with hardware interrupts? So hardware interrupts, unless you specifically manually kind of disable it, will have the highest priority always. So hardware interrupts will have the highest priority in most of the scenarios. Is RTOS being used in every communicational source and digital services? In many of them, yes. It depends. So some companies have their own versions of our real-time operating system running. Some of them try to just use a timer and write their own scheduler that does basically RTOS like stuff, but they don't use any proprietary RTOS and other things. On RTOS in automobiles and roles of task priority. Okay, so in automobiles, it differs from company to company. These automobile industry has very standard protocols for all this. They also intensely use the scheduler using the timer, and basically that's about it. So each company has their own. So there are multiple standards that an automobile industry has to meet, and it's a bit complicated to get into. So I will avoid going into more detail into that. But basically, there are compliances, there are UDS, there is basically Universal Diagnostic Service and other critical functions that have priorities, etc. To execute the interrupt, do we? Oh, I answered that. How does interrupts work in terms of what? How would it be difference in function which is called every seconds and RTOS? And could you please share some resources from where we can? Okay, so to study about the RTOS further, you can go to the free RTOS website. You can use YouTube. There are a bunch of tutorials, especially from DigiKey, etc., available, where they go into the implementation, like is how you write the code using your Arduino and ESP32 on RTOS. Then coming towards the first question, how does interrupts work in terms of electronics? So what interrupts is basically I configure a particular register. So let's assume I have a program counter. So how your program is executed is basically you have a program counter that executes instructions line by line, line by line, line by line in your loop. Whenever an interrupt occurs, the program counter is shifted to the location of the interrupt, and it executes the data there. After the interrupt is done, the program counter is shifted back. That is how they work. There are a bunch of resources regarding interrupts online as well. Even you can go into the Atmega 328P datasheet. The Atmega 328P datasheet, the 328P is the IC that is used on your Arduino Uno. And that datasheet has excellent explanations of interrupts, hardware resources, and other stuff. It can reduce the latency between the tasks. Doesn't it make system more quick responsive, which is in essence a good thing? Yes, RTOS does can make sure your system's latency low, but only in scenarios where you have multiple high latency things executing. For most of the use cases, that we have been working on towards maybe your college projects and stuff, like unless you have multiple time critical tasks, it is better to not use the RTOS, because RTOS is pretty memory intensive as well. It is not a simple thing that you can directly implement. So there is one recommendation that I forgot to give, that basically Arduino Uno is very scarce on resources. It doesn't have much resources, much compute available. So it is not a very good idea to execute RTOS on Arduino, because the amount of resources that running the RTOS consumes is not worth it for using it with an Arduino, because Arduino is already low on resources. But you can use it with STM32, you can use it with ESP32, some modern controllers like RP2040 and others, where they have good processors and can execute multiple things at the same time. Okay, global variables are handled. Semaphores. Okay, sir, can you explain about task and priority? All the tasks execute their own priority based on all the tasks are executed on the select.
Okay, I think we can pause the
Yeah.
Q&A part.
Okay, sure.
So I've shared the MCQ link in the chat box. All of you are requested to use the same name which you have used in the WebEx, so that we can compare with the attendance when we are releasing the letter of participation. So make sure to fill in the same name and answer the questions, and we'll close it in 5 minutes. So it was started at 5:55. At 6 p.m. it will be stopped. So the link is shared in the chat box. So meanwhile, just a small announcement, like the current session, which was real-time operating system, the same thing you can find it in the e-Yantra website of the links and everything. You can go to the e-Yantra YouTube channel to see the recording of this session, and as well as for the next session, which is scheduled on next Thursday, which is on June 5. It will be on introduction to ROS2, that is robot operating system. So if you are willing to register, please go to the website e-Yantra.org, and then you can click on register button. So I'll just show it. You go to e-Yantra.org website. You can click on the events, and then on that you can select research talks. So on that, this page will appear, which is introduction to ROS2. So only 2 minutes are left. In fact, 1 minute. Make sure to submit it after attending all the questions.